All right, everyone, get ready. Because today we're taking a deep dive into a paper that's been creating quite a buzz in the AI world, self-rewarding correction for mathematical reasoning. We all know that large language models, those LLMs we all love to talk about, have become pretty adept at crunching numbers. But getting them to actually spot and fix their own errors, now that's a whole other challenge.
It really is, and this paper tackles it head-on. What's particularly fascinating here is that the researchers have developed this framework they call self-rewarding reasoning. It essentially allows LLMs to act as their own internal critics.
So it's like giving these LLMs a superpower. They can generate a solution to a math problem, evaluate their own answer, and even revise it if they detect a mistake, all without needing any external feedback. That's pretty incredible.
It is. Imagine a single LLM that can do all of that. It's like having a student who not only solves the problem, but also grades their own work and then goes back and corrects any mistakes they find. Talk about efficiency.
Okay, I think it's time for a quick TLDR for our viewers who are all about efficiency and want the key takeaways up front. This paper introduces this brand new framework, self-rewarding reasoning, which essentially empowers LLMs to become their own judges and juries.
Exactly. They can generate those step-by-step solutions, decide whether their answer is a thumbs up or a thumbs down, and even go back and make those corrections when necessary, all without needing a separate reward model. It's a game changer in terms of efficiency.
So how do they actually achieve this? What's the secret sauce behind this self-rewarding magic?
Well, they use a very clever two-stage training process. The first stage involves a method called sequential rejection sampling. It might sound a bit intimidating, but it's actually quite intuitive.
Break it down for us. What's happening in this sequential rejection sampling stage?
Imagine you're holding a talent show, but only the contestants who can perform well and also identify their own mistakes make it to the next round. It's tough competition.
So they're training the LLM on a data set that showcases both correct reasoning and the ability to successfully self-correct. It's like showing the LLM a highlight reel of good and bad problem solving so it can learn from those examples.
Precisely. And then, in the second stage, they fine-tune the LLM on this very carefully curated data set, specifically honing its ability to recognize errors and make those crucial improvements.
And the results don't leave us hanging.
The results are quite impressive. These self-rewarding models are significantly outperforming existing self-correction techniques. They're showing remarkable improvements in both accuracy and efficiency.
So it's not just a theoretical concept. They've actually demonstrated that this works in practice. That's what we like to see.
Absolutely. And here's the best part. They've shown that this approach works across different LLM architectures like Llama and Qwen. That means it's not limited to a specific type of model.
So for those of you sticking around for the deep dive, we're about to peel back the layers and see how this self-rewarding magic actually happens. Get ready to explore the inner workings of this groundbreaking framework.
One of the really clever innovations in this paper is how they use this token prediction approach to teach the LLM how to assess its own work.
Token prediction. So we're not just talking about the LLM spitting out an answer. It's actually learning to analyze and understand its entire reasoning process.
You got it. They're prompting the model with very specific questions like, is the most recent final answer correct? Yes or no? And during training, they're guiding the LLM to output these particular tokens like verify correct or verify wrong based on whether the answer is actually right or wrong.
Okay, I'm starting to see how this works. It's like they're training the LLM to associate those specific tokens with the concept of accuracy.
Yeah.
It's almost like training a dog to sit, but instead of a treat, they're using these tokens as rewards.
That's a great analogy. And to really solidify the self-correction capability, they introduced this technique called sequential rejection sampling, which acts like a rigorous quality control process.
It sounds intense. So it's not enough for the LM to simply guess at an answer and then tell us whether it thinks it's right or wrong. There's a deeper level of scrutiny going on here.
Absolutely. Imagine you're training a robot to sort Lego bricks by color. You wouldn't simply accept any random pile it assembles, right? You'd carefully inspect each attempt, keeping only the ones where the robot correctly identifies and separates the colors. That's essentially what this sequential rejection sampling does. It's like a masterclass in quality control for LLMs.
So it's all about weeding out those problem-solving attempts that don't meet the mark. They're basically saying, hey, show us your work, and if you haven't spotted and corrected your mistakes, you're going back to the drawing board.
Exactly. This meticulous selection process creates a data set of those top-notch problem-solving trajectories that become the LLM's training ground for mastering that self-rewarding superpower.
This is where things start to get even more interesting. They don't stop at carefully selecting the training data. They also bring in the big guns, reinforcement learning techniques like DPO and PPO to further boost the model's self-correction game.
You're absolutely right. DPO and PPO are both powerful tools in the world of AI, each with its own strengths. DPO, or direct preference optimization, is like having a coach who helps the LLM choose between different problem-solving approaches. It's all about making those strategic decisions to increase the odds of success.
Okay, so DPO is like a strategic advisor. What about PPO? Where does it fit into the picture?
PPO, or proximal policy optimization, is more about fine-tuning the LLM's actions at each step of the problem-solving process. It's like having a personal trainer who pushes the LLM to refine every move, ensuring each step leads it closer to the correct solution.
Got it. So DPO is the strategist and PPO is the meticulous coach. But the burning question is, which one proved more effective in this self-rewarding scenario?
That's a great question. In their experiments, they found that PPO consistently outperformed DPO for this specific task. It was like PPO had a slight edge in this particular training arena.
Any theories on why PPO emerged as the champion in this case?
Well, one possible explanation could be the nature of the problem domain. Remember, we're dealing with mathematics here, where there's typically a clear-cut right or wrong answer PPO, with its focus on optimizing those actions based on these absolute rewards, might be particularly well-suited for this kind of environment. It's like PPO thrives in situations where there's that definitive ground truth signal to guide its learning process.
Makes sense. PPO loves those clear-cut scenarios.
Yeah.
But hey, let's not completely dismiss DPO. It's still a powerful tool, and I'm sure there are other situations where its preference-based approach really shines.
Absolutely. In fact, the paper explores how they used both PPO and DPO to push the boundaries of those self-rewarding capabilities even further, especially when it comes to tackling more real-world problem-solving scenarios.
All right, so we've covered the training process, but I know everyone is on the edge of their seats wanting to know, did all this fancy training actually pay off?
Yeah.
Did these self-rewarding models live up to the hype?
Well, in short, they absolutely did. And they didn't just meet expectations, they exceeded them. They put these models through a rigorous battery of benchmark data sets. Match 500, Olympiad, Bench, Minerva, Math, you name it. They tested it. And across the board, the self-rewarding models consistently outperformed those baseline models, both in terms of getting that final answer right and in their remarkable ability to catch and correct their own mistakes along the way.
So this wasn't just a theoretical victory. The self-rewarding framework actually delivered when it came to tackling those real-world problems. That's what we like to see, real-world results.
Precisely. And it's important to highlight that these weren't just marginal improvements. We're talking about significant leaps forward, especially when it came to those models going from an initially incorrect answer to a final correct solution. That's a testament to the effectiveness of that self-correction mechanism.
It sounds like these models are becoming quite the critical thinkers. They're not just stumbling onto the right answer. They're learning to actively evaluate their own reasoning and make those essential adjustments. This feels like a major step toward building AI agents that are not only capable, but also more reliable and trustworthy, which is something we all want to see, right?
Absolutely. But remember, we're still in the world of AI where perfection is often a moving target. While the overall results were pretty remarkable, there were some interesting quirks and challenges the researchers had to address. For instance, they observed that Qwen, even with all that careful training, sometimes displayed some, let's say, unconventional behaviors.
Uh-oh. Sounds like Qwen might have a bit of a rebellious streak. What kind of mischief was it getting into?
Well, they found that Qwen occasionally had this tendency to skip that self-evaluation step altogether, or sometimes it wouldn't format its answers in the expected way. It was like Qwen was trying to bend the rules a bit.
So Qwen needed a little extra guidance to stay on track. Did they manage to rein in its rebellious tendencies?
They did. They introduced this simplified two-turn conversation framework with much more explicit user instructions. It's like giving Qwen a clearer roadmap, breaking down that problem-solving process into distinct steps with very specific guidelines. No room for creative interpretation.
So they provided Qwen with a bit more structure and hand-holding to make sure it followed the rules and diligently performed those self-correction steps. It's like a smart approach.
Precisely. But let's not forget another crucial factor in all of this computational cost. Generating those extra responses for self-correction could potentially become computationally expensive, right? Especially as these models grow larger and more complex.
Absolutely. Efficiency is always a key consideration in AI. So did they find a way to address this potential bottleneck?
They did, and in a very ingenious way. They anticipated this challenge and built in a mechanism to dynamically adjust the computational budget during inference.
Dynamic adjustments. So they're not just generating a fixed number of responses every time. That's smart.
You got it. Remember how we talked about the model's ability to stop early if it's feeling confident about its initial answer? Well, that plays a crucial role here. It means that for problems the model can solve easily, it doesn't waste precious computational resources on those unnecessary self-correction steps.
Okay, I see the brilliance in that. It's like the model is saying, hold on a second, I'm pretty sure I nailed this one. No need to overthink things and burn through all that computing power.
Exactly. This dynamic scaling makes the whole self-correction process much more efficient, especially when dealing with those more straightforward problems that the model can handle with ease.
That's a fantastic optimization. So we've covered the training process, those impressive results, and even tackled some of those practical challenges. But now I'm ready for the main event. How about we dive into a specific example to see how one of these self-rewarding models actually tackles a problem? Let's see it in action.
That's a great idea. Let's bring this whole concept to life with a real-world example. But before we jump into the nitty-gritty of problem solving, let's remind everyone that we're not just talking about a single model here. The researchers tested this framework on different LLMs, including Qwen and Llama. What were some of the key differences they observed between these two architectures?
Good point. While the overall framework seemed effective across both Quinn and Llama, I'm curious to hear about those subtle but interesting differences in their behavior. We already touched on how Quinn can be a bit of a rebel. What about Llama? How did it fare in this self-rewarding arena?
You're right, each model had its own strengths and quirks. Llama, in contrast to Qwen, tended to be a bit more disciplined, consistently following those instructions it was given. However, it sometimes struggled to reach the same level of accuracy as Qwen, particularly when faced with those trickier math problems. It was like Llama was the diligent student, always following the rules, but maybe lacking a bit of that extra problem-solving flair that Qwen seemed to possess.
So it sounds like a classic case of different personalities in the AI world. Qwen, the creative rule bender, and Llama, the disciplined follower. But the important takeaway here is that the self-rewarding framework, regardless of the underlying model, consistently led to improvements across the board.
Exactly. Now, with that in mind, let's dive into that example I mentioned. This particular case really highlights the power of self-evaluation when the model initially stumbles upon an incorrect solution, ready to witness the magic of self-correction in action.
Absolutely. Let's see this self-rewarding brilliance in action. Bring on the example.
Okay, picture this. The model is presented with this problem. 3 positive integers, a, b, and x, form an O'Hara triple, abx, if the square root of a plus the square root of b equals x. For example, 1, 4, 3 is an O'Hara triple, because the square root of 1 plus the square root of 4 equals 3. If 36, 25x is an O'Hara triple, determine the value of x.
All right, a classic algebra problem to really put those LLM reasoning skills to the test. So what happens next? Walk us through how the model approaches this.
So, the model, following those chain of thought prompts, starts by laying out its reasoning step by step. It substitutes those given values into the equation, simplifies the square roots, and arrives at an answer pretty confidently, I might add.
So far, it sounds like smooth sailing on this problem-solving journey. But I have a feeling there's a twist coming up, right? This is where things get interesting.
You're absolutely right. This is where that self-rewarding element kicks in. Instead of just assuming its answer is correct and moving on, the model takes a moment and does that crucial self-evaluation. It asks itself, is my most recent final answer correct? Yes or no?
Okay, so the model is putting itself to the test. In this specific case, what's the verdict? Did the model pass its own evaluation?
Well, in this instance, after carefully examining its own reasoning, the model determines that its initial answer is actually incorrect. It gives a resounding no.
Wow, the model actually caught its own mistake. That's some impressive self-awareness. But what happens next? Does it just admit defeat and give up?
Not at all. This is where that clever two-turn conversation framework we talked about earlier comes into play. Remember, based on the model's self-evaluation, we give it a specific instruction to guide its next steps. In this case, the instruction is, since your initial response is self-evaluated as incorrect, there might be an error in the solution above because of a lack of understanding of the question. Please correct the error, if any, and rewrite the solution.
Ah, so the model gets a chance to redeem itself. It's like a second shot at cracking the problem. But this time, it's armed with the knowledge that its first attempt was off the mark.
Exactly. And thanks to all that training on those self-correction trajectories, it knows exactly what to do. It meticulously goes back over its previous steps, double-checks every calculation, and ultimately pinpoints that error in its reasoning.
Fingers crossed that it manages to work out the kinks and land on the correct solution this time.
And that's exactly what happens. By leveraging those self-rewarding and self-correction skills, the model successfully navigates the problem and arrives at the right answer.
That's pretty incredible. It's like watching a student learn and improve in real time. Except in this case, the student is an AI model capable of these remarkable feats of self-reflection. It's pretty mind-blowing when you think about it.
It really is a testament to the power of this framework. It's a big step towards creating AI agents that are not only smart and capable, but also possess those critical thinking skills to spot and fix their own errors, which ultimately leads to more reliable and trustworthy AI systems, something we all want to see.
Absolutely. We've seen how self-rewarding reasoning can lead to more accurate problem solving. But what about the efficiency side of things? You mentioned earlier that this approach can actually save on computational resources. Can you break that down for us?
Of course. One of the key advantages of this self-rewarding framework is its ability to dynamically scale the computational budget during inference. Basically, it means that the model doesn't have to use the same amount of computational effort for every problem it encounters.
So it's not just running at full speed all the time, no matter how complex the problem is. It's actually adjusting its effort based on how confident it feels.
Exactly. Remember that ability to stop early if it's confident in its initial answer. That plays a key role in optimizing those computational resources. For problems the model can solve easily, it doesn't waste time and energy on unnecessary self-correction steps.
That's a pretty clever strategy. It's like the model is saying, hey, I'm sure I got this one right. No need to overthink it and burn through all those computing cycles.
Precisely. And the beauty is that this dynamic scaling doesn't sacrifice accuracy. In fact, the paper shows pretty convincingly that these self-rewarding models can achieve higher accuracy than those traditional methods while using significantly fewer samples, which means less computational overhead. A win-win situation, really.
So not only are we talking about smarter AI, we're also talking about more efficient AI. I like the sound of that.
Absolutely. Efficiency is only becoming more important as we develop more complex AI models and tackle more challenging problems. This self-rewarding framework offers a promising way to create AI systems that are both intelligent and computationally frugal.
Now, before we wrap up this discussion, I think it's important to remember that this research, while super exciting and groundbreaking, is still relatively new. There are still plenty of unanswered questions and areas to explore. This is really just the beginning.
You're absolutely right. This is just the tip of the iceberg. This research opens up all sorts of possibilities and raises a bunch of intriguing questions for future investigation. What are some of the areas you're most curious about?
For me, one of the most fascinating aspects is the potential to extend this self-rewarding framework beyond just math. Could we apply these same principles to things like language translation, code generation, or even making AI more creative in tasks like writing? The possibilities seem endless.
Those are great questions. Just imagine the potential if we could give AI systems the ability to self-evaluate and self-correct across a whole range of domains. It would be a real game changer in how we develop and use AI.
It feels like we've unlocked a new level of AI capability, and we're just starting to understand the massive potential it holds. It's a pretty exciting time to be following AI research.
I couldn't agree more. And this paper is a testament to the ingenuity and creativity of researchers in the field of AI. It's a reminder that we're constantly pushing the boundaries of what's possible, and the future of AI is full of amazing discoveries just waiting to be made.
Another area I'm particularly interested in is developing even more robust and sophisticated reward models. While the researchers in this paper made some great progress, there's always room for improvement.
Absolutely. The reward model is so essential for guiding that self-correction process effectively. Having more advanced reward models could lead to even more accurate and nuanced self-evaluations, which would make these AI systems even more reliable and high-performing.
And let's not forget the crucial role of training data. The quality, diversity, and sheer volume of data used to train these models will have a huge impact on what these self-rewarding AI agents can achieve.
No doubt about it. High-quality training data is the foundation upon which these sophisticated models are built. The more diverse and representative that training data is, the better equipped these AI systems will be to handle real-world complexities and apply their learning to new and unexpected situations.
Well, it sounds like we have a lot to look forward to in the world of AI research.
Sure.
This self-rewarding framework is truly a game changer, and I'm eager to see what innovative applications and breakthroughs emerge from this line of research.
I completely agree. It's a truly thrilling time to be at the forefront of AI innovation. As we delve deeper into the nuances of these self-rewarding mechanisms, we're paving the way for AI systems that are not only capable, but also more reliable, efficient, and maybe even a little bit more introspective.
And on that note, we'll wrap up this deep dive into the fascinating world of self-rewarding AI. A huge thank you to the researchers for their groundbreaking work, and to all of you for joining us on this exploration. We'll see you in the next episode of AI Paper Podcasts, where we'll continue our journey into the cutting-edge advancements shaping the future of artificial intelligence.
Thanks for having us. Until next time, keep exploring the world of AI. Okay, let's actually walk through an example to really illustrate how this self-correction process works in action. Imagine the model is given this problem. 3 positive integers, a, b, and x, form an O'Hara triple, abx, if the square root of a plus the square root of b equals x. For example, 1, 4, 3 is an O'Hara triple because the square root of 1 plus the square root of 4 equals 3. If 36, 25x is an O'Hara triple, determine the value of x.
All right, a classic algebra problem to put the LLM's reasoning through its paces. What happens next? How does the model tackle this?
So the model, using those chain of thought prompts, starts by methodically outlining its reasoning step by step. It plugs those given values into the equation, simplifies those square roots, and comes up with an answer pretty confidently too, I might add.
Sounds like a pretty straightforward problem-solving process so far, but I have a hunch that this is where things take a bit of an unexpected turn. This is where we see the self-correction in action.
Exactly. This is where that self-rewarding element really shines. Instead of just assuming its answer is correct and calling it a day, the model pauses and goes through that critical self-evaluation step. It asks itself, is my most recent final answer correct, yes or no?
So the model's putting itself to the test. What's the verdict in this case? Did it pass its own evaluation?
Well, in this scenario, after carefully going over its own line of reasoning, the model determines that its initial answer is actually incorrect. It gives a clear no. It realizes it made a mistake.
Wow, that's some serious self-awareness. The model caught its own error. It's almost like it's got this built-in error detection system. But what happens next? Does it just throw in the towel?
Nope, not at all. This is where that two-turn conversation framework we discussed earlier comes into play. Based on the model's self-assessment, we give it a specific instruction to guide its next steps. In this case, we tell it, since your initial response is self-evaluated as incorrect, there might be an error in the solution above because of a lack of understanding of the question. Please correct the error, if any, and rewrite the solution.
So the model gets a second chance to get it right, like a problem-solving do-over. But this time, it knows that its first approach was flawed.
Exactly. And thanks to its training on those self-correction trajectories, it knows what to do. It diligently revisits its previous steps, scrutinizes those calculations, and finally pinpoints where it went wrong in its reasoning.
Let's hope it manages to iron out those wrinkles and arrive at the correct solution this time.
And that's exactly what happens. By using those self-rewarding and self-correction abilities, the model successfully works through the problem and arrives at the right answer this time.
It's like watching a student learn and adapt in real time, constantly refining their understanding. Except, in this case, the student is an AI model capable of these impressive feats of self-reflection. Pretty amazing when you think about it.
It really showcases the power of this framework. It's a significant step towards creating AI agents that are not only intelligent, but also have those critical thinking skills to identify and correct their own mistakes, which ultimately leads to more reliable and trustworthy AI systems, which is what we all want to see.
Absolutely. We've seen how this self-rewarding reasoning can lead to more accurate problem solving. But what about the efficiency aspect? Earlier you mentioned how this approach can save on computational resources. Can you explain that a bit more?
Sure. One of the major advantages of this self-rewarding framework is its ability to dynamically scale the computational resources used during inference. In simpler terms, this means that the model doesn't use the same amount of computational effort for every problem it encounters.
So it's not just going full throttle all the time, regardless of how complex the problem is. It's actually adjusting its effort based on how confident it is in its solution.
Exactly. Remember how we talked about the model being able to stop early if it's confident in its initial answer? Well, that's a key part of optimizing computational resources. For those simpler problems that the model can easily handle, it doesn't waste time and energy on unnecessary self-correction steps.
That's a really smart approach. It's like the model saying, hey, I'm pretty sure I nailed this one. No need to overthink it and use up all that computing power.
Right, and what's really impressive is that this dynamic scaling doesn't compromise accuracy. In fact, the paper shows that these self-rewarding models can actually achieve higher accuracy than those traditional methods while using fewer samples, which means less computational overhead. A win-win situation for sure.
So we're not just talking about smarter AI, we're also talking about more efficient AI. That's definitely a step in the right direction.
Absolutely. Efficiency is becoming increasingly important as we develop more complex AI models and work on solving even more challenging problems. This self-rewarding framework provides a very promising path towards creating AI systems that are both intelligent and computationally frugal, a very attractive combination in the world of AI.
Well, it seems like we've only just scratched the surface of what's possible with self-rewarding AI. This framework is a real game changer, and I'm excited to see what new applications and breakthroughs come out of this research in the future.
I completely agree. It's a really exciting time to be involved in AI research. As we continue to explore these self-rewarding mechanisms, we're opening up so many possibilities for creating AI systems that are not only capable, but also more reliable, efficient, and maybe even a little bit more introspective.
And on that note, we'll wrap up this deep dive into the world of self-rewarding AI. A huge thank you to the researchers for their amazing work and to all of you for joining us today. We'll see you in the next episode of AI Paper Podcasts, where we'll delve into another cutting-edge development in the ever-evolving world of artificial intelligence.
It's been a pleasure. Until next time, keep those AI algorithms running.